1545. We are given this spherical shell, which means that the charge is only on this thing, but there's nothing inside and there's nothing out here, which carries a total charge of minus Q. He doesn't give an actual number, but it is uniformly distributed. There's no blobs of greater charge anywhere than anywhere else, with a radius of A. So the first part of the problem asks for the electric field somewhere outside the shell, like there, at a distance perhaps r from the center. Okay, well, if I were to look at each of the little tiny pieces of this sphere as if it were a point and find the contribution from this one, and then from that one, and then from this one, and from the one up here, I'd need to use calculus to add them all, and it would become a very, well, tedious and annoying problem to say the least. But since this sphere is uniformly charged, the electric field here should point directly away from it. If I look at a point over here, also distance r from the center, the electric field should point away from the sphere and be the same size as the electric field here. In fact, if I look at the electric field anywhere, a distance r from the center of the sphere, like say there, it should still point directly away and be the same size as the other ones. I could connect all those points in a imaginary spherical surface surrounding the shell of charge. So all the electric field anywhere on that dotted circle, or in the sphere that I didn't try to draw, should have the same size and point directly away from the center. That fact perhaps will help us use maybe Gauss's law, which says an ugly integral, which is equal to the net flux through a closed surface, is equal to the charge inside the surface divided by epsilon 0. Well, the charge inside the surface is easy. The dotted line is here. The charge inside it is everything on this minus Q. So the flux is just minus Q over epsilon 0. All we have to work out now is this integral on the left-hand side. We need first E dot dA. Well, let's see. Right here, the area vector is outward perpendicular to the sphere, so in that direction. Right here, the area vector is outward perpendicular to the sphere, well, that way. Over here, the area vector is outward perpendicular to the sphere, that way. In fact, no matter where I do that, the area vector and the electric field vector are parallel. So this works out to the magnitude of E times the size of the little piece of area times cosine of 0, which is just E dA. So if I put that back in our integral, we have E dot dA for our particular case is now just E dA. Oh great, so we got rid of some vector signs and a dot. Still looks like an ugly integral. But remember, the electric field size is the same here as there and as over here and anywhere else on the dotted sphere. So this E is a constant, which I can take outside the integral, which makes E times the integral of all the little pieces of area. And what do you get if you add up all the little pieces of area all around a big sphere? You just get the surface area, which for a sphere is 4 pi r squared. Now that is the radius of our imaginary sphere here with the radius little r, not the area of the charge. So the integral works out to 4 pi r squared E. The right hand side is minus Q over epsilon 0. All I have to do is put them both together. So 4 pi r squared E is equal to minus Q over epsilon 0. So if I solve for E, you get minus Q over 4 pi epsilon 0 r squared. Now the minus sign just means that this is a negative charge, so while we've been saying the electric field points directly away, it actually points opposite that direction, hence the minus sign. So the electric field vector is actually inward. E would be Q over 4 pi epsilon 0 r squared in. Then part B asks us to find the electric field at a point r from the middle, but that is inside the shell. So I guess this is R1 and that's R2 for part B. Now I can do the same thing find a spherical shell that includes that point. And then on the right hand side of Gauss's law, Q enclosed over epsilon 0 would be the charge inside that little imaginary sphere. However, all the charge is out here on the shell. None of that is inside here. So for part B, Q enclosed is nothing. And if I add up a bunch of stuff times something that's not 0, because that imaginary sphere does have area, but yet we have to get 0, that means what we're adding up itself must be 0. So for R is less than A, or inside the shell, E must in fact be 0.